Hi everyone, my name is Choong-Wan, and today I'm going to talk about good practices in developing neuroimaging biomarkers, and this was the talk that I gave at OHBM 2020. And I wanted to share this with all of you, so I'm re-recording it. So the use of machine learning in translational neuroimaging has rapidly increased in recent years, showing its increasing popularity. And it is because of the power of neuroimaging and machine learning techniques. First, the functional neuroimaging, especially fMRI, allows us to do systems level brain imaging with a reasonable spatiotemporal resolution. And it also provides a unique opportunity for multi-species neuroimaging with which we can translate research findings from animal to human studies and human studies to animal. And with machine learning, we can now model high-dimensional data such as functional neuroimaging data and to predict some useful outcomes of interest. And the combination of these two powerful methods provides a pathway to clinical translation, serve as a bridge between the preclinical and clinical studies. However, not many clinical tools are available yet, and I want to discuss how we can improve this situation. There could be many different reasons, but my take on this have three main proposals. And the first one is treating neuroimaging maps as research objects. This plot shows the survey results from a recent review paper, and this shows the classification performance of the neuroimaging models for different brain disorders. The first look seems not that bad, and there seems to be many good models. However, this is the results at the model development stage, that is with training data. If we put this within the biomarker development framework, where most promising models should be carried forward until we achieve the population level generalization, we can find most of the models are stuck at the model development stage. And there could be many reasons for that, and you might think that the sample size, that is the amount of data, might be the biggest challenge here. However, when we isolate the multi-site studies, which should have enough data, you can see that sample size is not the main issue here. The proportion of the studies with prospective testing was low, even for multi-site studies. And the model performance with the prospective testing was lower than the performance at the model development stage, suggesting that there is a clear bias in the study. Interestingly, when we examine the promising models that went through the prospective validation and robust replication, many of them had their names, showing the researchers' intention to share these models, and they treated these models as research objects. So when I shared this interesting observation to my colleagues a while ago, one of them taught me about the boundary object. The boundary object is a term from sociology and indicated an object that could be used in different ways by different groups. The objects are plastic but robust enough to maintain their integrity. So what I proposed is that we need to treat brain maps as boundary objects that can be used differently by different groups. So cognitive neuroscientists can use them to reveal the brain mechanisms, while clinicians can use them for diagnosis. And to promote these flexible uses of the brain map, we need to share our maps and models through these different platforms like NeuroVault, GitHub, and Figshare. And recently I came across this tweet that was advertising a meeting, and I liked its title, Scientific Publication Beyond the Text, Sharing Research Objects. By treating brain maps as research objects, we will be able to make the science of neuroimaging more than bigger than publication. And second, we need to focus on clinical utility. So if you examine what the machine learning models were designed for in many translational neuroimaging research, you can see most of them were designed for diagnosis. But will these diagnostic models be clinically informative? I don't think so, because there are already many available and cheaper options for diagnosis. Rather, we believe that these 25% of uses, including predicting treatment response, prognosis, etc., will be more useful. What I want to emphasize here is that the accuracy is just one among many factors that can influence machine automation and clinical translation. So in this machine automation map, there is additional factor, risk, in addition to the accuracy. For example, credit card fraud detection has very low accuracy, but the risk is also very low. Therefore, it has already been implemented and used in the real world. However, driverless cars already achieved high accuracy, but because of the high risk, it hasn't been automated yet. Similarly, I think the clinical utility should be an important factor for clinical translation in addition to accuracy. So for example, even though diagnostic test has a high accuracy, because of its low clinical utility, it won't be translated easily, but early detection and risk assessment could be translated more easily even with their low accuracy because of their high clinical utility. Therefore, we need to concentrate our efforts on neuroimaging models with high clinical utility. The last point is that we need to make advances in the knowledge of human brain. So that is related to the issue of interpretability or interpretation of neuroimaging-based machine learning models. And these models, even with linear methods, are highly complicated. And therefore, it is quite difficult to know why and how the model works. But if we cannot answer these, we cannot know when the model will fail, to which individuals or subgroups it applies, and how it can advance our understanding of the neurobiological mechanisms. For a model to be interpretable, it should be A, readable and understandable to humans, B, provide useful information about neural representations, and C, show the predictions are based on true signal, not noise. So in our recent paper, we approached this problem with a multi-level model interpretation framework, and in this, we divided the assessment into 3 different levels. One is feature level, 2, model level, and 3rd, biology level. The biology level assessment is most difficult, and if the existing literature cannot explain the model, we should push the boundary of the current knowledge and pursue the new discovery and theory development through new experiments. In the first table of this paper, we added detailed explanation of each level assessment with references for the example methods so that you can find the details later. One last proposal is the component process approach. The direct prediction approach uses the neuroimaging features to directly model clinical outcomes. But in the component process approach, we can first model the component processes that are more closely linked with brain functions, and then use them to model more complex clinical outcomes. And this is an analogy where the direct prediction approach is a gray scale because it is using one-dimension scale, while the component process approach is the RGB color scale, where we can use these component processes we can use these component process markers to draw more complicated colors like clinical outcomes. With this component process approach, we might be able to connect the Death Valley of translational research. These component process markers would satisfy neuroscientists or cognitive neuroscientists because it can It can be used to study brain mechanisms, and also could satisfy clinicians because it can also serve as ingredients to explain more complicated clinical features. So that's all for my take, and there is another recommended reading, a blog post by Peter Bandettini. I read this blog post today again, and it was worth reading. So these are the summary recommendations that I wrote in the abstract, OHBM abstract, and I already explained them above. So I only repeat them here, but you can read this. So thanks for listening, and thanks to Choong-Wan Lab and Can Lab. Thank you guys. Bye.